All right, we're going to start with a little easy warm-up. So everything in this video should be pretty much something you've seen before, done before at some point. We're just going to get some practice because it's going to be really important as a foundation going forward. Okay, so remember that solving an equation is just finding something that makes the equation true. And now that our solutions are going to be functions, we also want to make sure that it's true for all values of that independent variable. So we're going to start by looking at a differential equation. Let's say this is dy dt equals y squared minus 1 over t squared plus 2t. And I'm going to ask, which of the following solutions to this differential equation? All right, and what I would really like you to do as I'm writing these down, I would like you to pause the video right now. I'm going to write some equations down, or some functions down, and I want you to pause the video and check, because you all know how to check right now. We talked about that in the previous section. You can check by just look at the left-hand side, look at the right-hand side, and see if they're the same thing. I will go through the whole answer, so once you've paused the video and worked things out, we'll move on. And this is something I'm going to be trying to do a lot during this class. It's really important that you're pausing the video, writing questions, writing notes, trying to work out solutions. Don't just watch passively. Learning does not happen passively. So please do so right now. All right, so let's start by checking letter A. So for letter A, we're going to look at the left-hand side first. What's the derivative of y with respect to t for this y? Well, the derivative of this y with respect to t is just 1. Right? The derivative of this with respect to t is just 1. And the right-hand side is this. Well, if y is 1 plus t, what does this become? Well, we're going to have to do some algebra, right? There's going to be y squared, which is 1 plus t, minus 1, all over t squared plus 2t, right? We're just substituting this function in for y. And doing some algebra, we'll get 1 plus 2t plus t squared minus 1 over t squared plus 2t. And you're going to see something really interesting, right? We have a plus 1, we have a minus 1. And essentially the same thing that's on the top is on the bottom. So as long as t is not equal to 0, this is also equal to 1. This is equal to 1 as long as t is not equal to 0. And if t equals 0, then, well, then the original differential equation is not even defined in the first place. So this solution is true for everything where t is not equal to 0. Now, the second one, we'll go over here for letter B. It's going to be very similar, right? The left-hand side is the derivative. What's the derivative of this function with respect to t? It's 2. Now the right-hand side, again, you should be doing very similar situations, except you're going to get 1 plus 2t squared minus 1 all over t squared plus 2t. And when you do this, again, that's going to cancel out, but instead you're going to get 4t plus 4t squared all over t squared plus 2t. And this is going to be something a little bit different. We can factor out a 4t on the top, and we're left with a no t. We're left with 1 plus t. On the bottom, we can factor out a t, and we're left with 1 plus 2t. The t's are going to cancel. Let's make sure let's double check my quick math, right? 4t plus 4t squared, yep. And then t plus 2t, wait a minute. No, this is why you check your work, right? In the denominator, you factor out a t, you're going to get t plus 2. Excellent. Regardless, this is not equal to 2. There is a value of t for which this is equal to 2. So the left-hand side is equal to the right-hand side for some value of t, maybe multiple values of t. But it's not true. This is not equal to 2 for all t in the domain. So we're going to say, yep, letter A Yes, this is a solution. Letter B, no, this is not a solution. Okay? And we can look at letter C. The derivative of letter C is just 0. And when you plug in C into the right-hand side, you get 0. So letter C is a very quick yes. It's a very silly solution. It's an equilibrium solution, right? As t changes, the function's just constant. The function is never changing. This is a solution, never changes, equilibrium solution. If you found the equilibrium solutions, what would you do? You'd set the derivative equal to 0. And when you solved that, you would get y is equal to positive or negative 1 as 2 of your equilibrium solutions. So here are some solutions and one not solution of this differential equation. All right, so the other thing that we're going to practice, and before I go into the next thing, right, just really stress, this is one of the nice things about differential equations, is especially when you're doing analytic solutions, you can check your answer. It's just like Calc 2, right? When you're doing integrals, if you find an integral, you can always check your answer by taking the derivative. It's the exact same thing with this. Of course, yet another reason for why you should be practicing your derivatives and your integrals, because you're going to need to be able to do both. All right, so let's move on. Is my dog's whining getting picked up on this? That'd be interesting. We'll have a dog camera in future math videos, so you want to keep learning differential equations. The dog will make her appearance. All right, so let's do the last part of this so my dog doesn't have a heart attack. And do one more example, again, of something that you have probably seen before. The derivative of y with, let's say with respect to t, is equal to 12t cubed minus 2 sine of t. And I'm going to tell you that y of 0 equals 3. So what kind of problem did I call this? We called this an initial value problem because it's a differential equation, a first order ordinary differential equation with an initial condition. It's an initial value problem, an IVP. So we can actually find the general solutions and find the particular solutions of this equation. Because this is a very nice equation because we can just take the integral of both sides, right? Integral of the left-hand side with respect to t, we can find that no problem. Integral of the right-hand side with respect to t, we can find that no problem. The left-hand side is just y plus some constant. The right-hand side, we'll use the power rule. Add a power, divide by that power. Antiderivative of sine is negative cosine. And that's also plus some other constant. We can subtract the constant from the other side, and we're going to get 3t to the 4th power plus 2 cosine of t. And then again, we have some new constant, right? A constant minus a constant is still just some other constant. And we often don't even write all these constants. We'll just say plus c usually, right? And we can check our answer, right? The derivative of this is 12t cubed minus 2 sine of t. Perfect. That's exactly what we wanted. This right here is the general solution. And we can find the particular solution using the initial condition. So we know, right, that when, let's use a different color for that. We know that when t is 0, y is 3. So we just plug that in. 3 times 0 to the 4th plus 2 cosine of 0 plus some constant. And again, this is all 0. This just becomes 2. And you get 3 is equal to 2 plus that constant. That constant is just 1. And that allows us to find our particular solution. And that'll be our final answers, right? Here's our general solution. And our particular solution is 3t to the 4th plus 2 cosine of t plus c, which we said was 1. For this initial condition, our constant is 1. So we know how to check our answers for a differential equation. We know how to check whether something's a solution or not. Make sure it's a solution for all t. And we found out how to go from a general solution to a particular solution by using our initial condition. Tune in for the next video for more fun stuff. We're going to talk about what is a separable equation. We're talking about separation of variables. What does it mean to be able to separate? So that'll be next. And then we'll start solving things in the one after that. Bye-bye.